Hi, this is Abir Ahmed again, and this is the lecture 2. So in this lecture, I'm gonna show you about finite difference theory. That means how you can replace a derivative or second order or first order, it doesn't matter, any order derivative by a finite difference approximation. So in this lecture, I'm gonna show you all these things here. Okay. So in the previous lecture, I have already said that these are one of the important equations, and these are the derivative, right? So we have to replace these derivatives by a finite difference approximation so that we will get a finite difference approximation equation. So this is the equation of heat equation, right? So I'm gonna write this equation in terms of finite difference approximations, how we can do that. Okay, so before going through this, we have to understand about the interpolation and the Taylor series expansion. Okay, so what is Taylor series expansion? Okay, in calculus, Taylor's theorem gives an approximation of a k times differentiable functions around a given point by kth or a Taylor polynomial. Okay, I'm gonna make it clear all about that. So Taylor series is nothing. Taylor series is one of the interpolation function, interpolators. For example, if it is x and if there is increment x plus a, then the difference between this point and this point is h, right? So, and we have here at this point x, if we have a function, for example, here is the color. If this is the function here, for example, here fx equal to if fx, okay, then we will get another function here in h plus fx plus h. Okay, yeah. So what is the value here? So it is the x minus h. So if we have a function, for example, fx equal to for example, we have a function for fx equal to x square plus 3x plus x square plus say 3x plus 4, something like that. So we have a function fx, so we'll get a value for I, for at value I we'll get a value of fx, right, at one is what we can get at fx x plus a point here, the same function. Okay, so this interpolation, right? So we want to determine the value at this point in terms of this point, right, in terms of this point's value fx. So the value of this point is fx plus h, right? Okay, so this is interpolation. So this interpolation can be made by using this point, or even we can, if we know the value of this point and if we know value of this point, then we can interpret what would be the value of this point here. So this is, so this interpolation is based on 2 point value, right? So and if we want to determine this value of this point, then we have to uh, depend on this, so on this value only, x point. So this is called the 1 point dependence interpolations. Okay, so we do have 1 point, 2 points, 3 points, even 6 points of dependence value here in MATLAB. So here in this mathematics. Okay, so what does Taylor series expansion? So we know this is the function at point x, right? So this is a function at point x. Okay, Taylor series expansion will do nothing but Taylor's theorem will express this function into a series related. Okay, so what we have got the value of this function at x is fx, right? So what we will get the value at x plus h of this function. Okay, so this is, so x naught, if it is not x naught, then we will get this x naught plus h value. So fx naught, that means these functions. So if this x naught function, this function, okay, this function plus first derivative of this function divided by 1 factorial into h, because we have the distance h here, right, plus second derivative of this function divided by 2 factorial into h square, plus and so on. Okay, so we can easily find out the value of nearest point using the neighborhood points. Okay, so this is the Taylor series expansion. So this is the Taylor series expansion, nothing else. So we can use this, we have to understand this Taylor series expansion to uh, understand the finite difference approximations. Okay. Before going through these lectures, I would love to say I have scanned all my lecture notes, all my class notes here, and I have scanned those for these lectures. And for convenient, I'm gonna using those lectures here. Sometimes you might think that it's boring or something like that, but I didn't have any opportunity uh, to write this types of functions. This is time consuming or something like that, so I think it'd be more convenient to you all. Okay, so final difference approximation, we are here. Yeah, okay, so consider a small increment del x equal to a. Okay, so we have already uh, uh, said, for example, here if it is a x, then there is a small increment x plus a, so the increment is 8, right? So increment is 8 here. Okay, consider a small increment a. So for in x in x direction, right? So this is the x direction, x, and this is the minus x, and this is the our origin point of x. So then definitely we have already seen that what is the Taylor theorem said, fx plus a is fx equal to something like that. So we are already introduced these functions. Okay, so from this Taylor series expansion, we can bring out we can find out easily the first derivative of the function, right? So f prime x, what does this mean? F prime x, so f prime x means the first derivative dy by dx. Okay, so dy by dx, right? So f double prime x means the second order function, second order derivative, uh, d square y dx square, right? Dx square. So this is the f prime x. So from this expansion, from this Taylor series, we can find out the derivative of this. Okay, so if we bring out this, and if we say uh, we can also say this is the error, truncation error. So if we avoid these terms, then we can if we avoid this, because these terms are very negligible sometimes. Yeah, this is that's why it is called truncation error. So we have three terms, fx plus a, x and h into first derivative of function, right? So we can write it here in this form, fx plus h, fx, so h into first derivatives and the other whole term. And if the whole terms are so from this equation we can find out, we can bring this out in left hand side. So f prime x equal to fx plus a minus fx equal to a plus this all other terms fx. So for example, if these all other terms or s tends to 0, then we will get f prime s approximate sign, this is not equal sign, this approximate sign fx plus h minus fx divided by h. And this is called the forward difference formula. Why it is called forward difference formula? Because uh, for a difference formula, because we are interested here, we are interested we're interested to find the value of x at point x on the basis of this x plus h point value, right? So this is the forward, one term forward here. So that's why it is called the forward difference formula. So we have got the value at point x on the basis of this next point value. Yeah, so this is forward difference formula. Similarly, if we expand x at x minus s, then we can write x minus s. Then here, if this is the x, this is the x minus x. If the distance between this point and this point is a, then we can write the Taylor series expansion like this way: fx minus a is fx minus a into, because a is equal to minus, right? So f prime x plus, why it is plus? Because a square, so minus a square equal to plus a square, same thing. So it is plus a square divided by 2 factorial into double derivative, second derivative of this function, and so on. So from this we can also write down here f prime x equal to fx minus fx minus h divided by h, and the all other terms. If all other terms are 0 here, then we'll get f prime x equal to fx minus uh, f x minus a is divided by a is, right? So from this, so this is the backward difference formula, because we have used the previous values to get the present situation or something like that at point x, right? Okay, same way this is the equation 2, right? And we have the forward difference formula. So if we differentiate, if we subtract this equation from the forward difference equation, then fx plus a's minus fx minus a's 2a's f prime x plus something like that, then we have got this f prime x equal to f x plus a's minus f x minus s divided by 2a's. Okay, and all the truncation error, if the truncation error or the remaining terms are zero, then we have got this. Okay, and this is called the central difference formula, because we have used the forward terms here fx plus a's, and the backward term here fx plus x minus s. So we are interested, so if this is the x plus a's, so we used both values, used x plus, we used both these days, we use the both values at this point to get or to derive the values at point x. So this is called x values or central difference values, and we do always use the central difference formula, because it approximates the more accurate results on the basis of two neighboring points, something like that. Okay, for two-dimensional we do use generally the 4 points here. Okay, I'm gonna show you all about this in two-dimensional in next lectures here. So we do use the 4 points for two-dimensional case, because it is the x-axis and this is the y-axis. Okay, so we have got three different formula, forward difference formula for the same thing. So we can write dy by dx equal to here. So we can write here f x plus a's minus f x minus a's divided by 2a. So sorry, we have replaced the derivative dy by dx by this approximation fx plus a's minus x minus a's divided by 2a's. So the distance between this and this is 2a's, because the a's and a's. Okay, we have got here, we have a value at point x plus a's. This is the function value, and this is the function value divided by the 2x. Okay, so we can get the derivative. So in the first lecture I have already said that we have to replace our derivatives by the finite difference formula, finite difference approximation. So this is the first derivative, and we have got this the finite difference approximation of the uh, first derivative of something, of any function. So this is a central difference. Okay, central difference formula. So we will have a backward difference formula if we write dy by dx equal to fx minus x minus a divided by a, and we have also the same the forward difference formula here. Okay, fx plus a minus a divided by a, something like that. Okay, so we have got three formula for this. So generally we do use the central difference formula here, central, because it approximates more accurate and more better results on the basis of the neighboring 2 points. Okay, okay, double derivative. So how we can replace our d square y divided by dx square? So what would be the result? Okay, so we are going to derive this formula. So if we add from 1 and 2 equations, that means the forward difference formula and the backward difference formula. So this one and the previous one, then we will get fx plus a's plus fx minus a's plus 2fx plus 2 into x square plus 2 factorial, second derivative of that function, plus 2, and so on. Okay, so from this we can bring this out and we can find the value right here, the second derivative. So fx plus a's plus fx minus a's minus 2fx divided by x square. Okay, this is the second derivative formula for second order equation. So we have got this equation f x plus a x plus f x plus a. So at this point f x plus a, so we write from here minus 2 times of the value at point here, 2 times the value at point here, fx. So this is the fx point, right? So 2 if this I'm sorry, I'm writing with my mouse, that's why my writing is not very good here. Okay, plus this point value. Okay, plus this point value. Okay, backward formula. Okay, divided by a square. Okay, divided by a. So this is, for this is the second order formula, something like that. So this is the second order derivative formula. This is second order derivative formula here. So we have replaced our first order derivative by our finite difference approximation. So we have also replaced our second order derivative using the by the finite difference approximation. So we can write. So these are two formulas here. So we can use this. So these are one important formula. So I'm gonna erase all these things. So this is the one equation, right? So this is the one another equation. So backward formula. So we have another other equation is equal to 0, and we have other equations in previous slide. Okay, so this is the for second order derivative, and this is the first order derivative. Okay, so generally in first order derivative we will use this equation and central difference formula, because central difference formula approximate more better results. Okay, this is second order derivative formula here in this. Okay, you have derived this. So in the finite difference method, we replace the derivatives that occurs in the ODE or PDE by the finite difference equivalence. Okay, we then write the finite difference equation corresponding to each grid point using the function values. The surrounding grid points, the solution, the situation. So we have already discussed all this, because we have to solve the equation in every and each and every grid, right? So if we have something like that, 2 grids or something like that, it is a grid. Okay. So we have several nodes here, right? So we have to solve this equation, heat equation, or it may be a Schrodinger equation, wave equation, Navier equation, whatever it is. We have to solve the equation in every grid point, okay, using the uh, central difference, backward difference, or something like this. And I'm going to show you how we can do that. Okay, so at first we have to learn how to replace the derivative by a finite difference approximation. So for example, we can use the following central difference approximation. Say, I'm going to show you here is the for f prime x equal to, the first order derivative x central is this is central, right? The mm, forward value at this point, something like this, yes. So definitely know all about this. Okay, yeah. So the given interval is divided into a subinterval something. Okay, I'm gonna show you a new. Uh, okay, Uh, mm, I'm gonna. Okay, I'm gonna pin new page. It has all options here. I've got a new page screen. Um, say what? I'm gonna show you how we can replace a derivative or something like that. Okay. So if we have equation, for example, dx by dy, it's arbitrary equation, say k into dy, sorry, say I'm gonna erase this. Say we have a function f, right? Say we have a function f. So this is a function, okay? So this is the function f. So for example, we have the derivative with respect to x. So we say we have equation, this one, number one equation. So how we can replace this? How we can replace this finite difference approximation? So we have a function f(x), right? So fx is partially derivative by with respect to y again with respect to x. So how we can write that? So for example, so if we use the central difference, if we use the central difference, then if it is x, if it is x plus a, this point, okay, and this x minus a, the value at point x is fx, right? The value at point this is fx plus a, right? And the value at point this is x minus a, right? Okay, so we want to determine the value at point here x on the basis of these two node values, something like that. Okay, so how we can do that? Okay, so we have to approximate, if we use the central difference formula, so fx by dy, we can write f the forward x plus a minus f x minus a divided by 2a, right? If this is the, if the distance between 2 points is a, right? Okay. Okay. This is the one-dimensional equation, so we cannot write. Um, we cannot write, so we have to modify the. If this is the second derivative, then we can write have something like that. So this should be modified something like this. So this is the x, because we uh, this is the x, so we get this. So we have to say, for example, we do not have this equation, because we are interested at first, we are doing in one dimensional equation, so we cannot do with respect to y, because we have to consider only the x, because this is the x direction only. Okay, so I'm gonna erase this. Okay, so I'm gonna write it in two dimensional. So for example, df d x square dx square. Okay, so our equation is something like this. So in it's all in here x, so it's one dimensional. Okay, so so what is uh, d square f by dx square? So what is d square f dx square? So using the central difference equations, we know central fx plus a, fx plus a minus 2 fx, right here. Okay, plus a x minus a divided by a square, right? So you have got the two approximation of this. So if we replace these equations here, so if we replace this here, so what we write? So we can write um, f x plus a minus 2 f x plus f x minus a divided by a square. So we can write here the first, this one, so k into k, second bracket, f x plus a minus f x minus a, right? Okay, so we have here a square and we have here a, so we can cancel out each other. So a, so if we take this a here, then it will be k a, so we have to erase this. Okay, I think you have understood this. Okay, so this one should be vanished out each other, vanished out each other, vanished out each other. Okay, so now if we write, so you want this equation, right? So you want to determine these values here. So what we can write here, so I can bring this out to right hand portion, and I can bring this portion to this is the second bracket. Okay, so if we take this here, so 2f(x) would be f(x) plus a plus f(x) minus a. This should become here minus k a f(x) plus a plus k a f(x) minus 8, right? So we can rearrange this equation. So um, yep, 2fx, something like this. So we can take fx plus a. So f x plus a, so we'll get 1 minus k a, right? Okay, so from this term and from this term. Okay, right? Okay, so similarly we can do that. F x minus a 1 plus k a. Okay, so we have derived this equation. So we have 2fx equal to something like that. So if we uh, multiply with this half, so we have to multiply with this half, so this should be the half, right? Okay, so we can get so from this equation we can make a matrix or something like that, right? It's very easy. So from that we can do. So in the next lecture I'm going to show you how we can so we have transformed this equation, right? We have a partial ordinary differential equation, and we have to transform this ordinary differential equation to a finite difference approximation, right? Here it is the finite difference approximation. So we can do that. So we have discretized our domain at first, then uh, we have discretized our domain into equal parts. Okay, then we have discretized, we have replaced our original equation to finite difference approximation right here, right? So finite difference approximation. So using this approximation we have to solve this equation in every node to get the values. Okay, to get all the values, something like that. Okay, so how we can do that? So we have a technique in matrix form, so we can do that in matrix. So if you do have any idea about matrix, then it'll be more easier for us to understand this. Okay, okay. So in the next lecture, what I am going to do, in the next lecture we have an example here. This equation for deflection of a beam is given by y double prime x, that means the second order differentiation equation, uh, minus e to the power x square equal to 0 when we have boundary condition. Boundary condition, that means y equal to 0, y equal to 1. So we have length 1, 0 to 1. Okay, 0 to 1. So at point 0 we have y, the value of y is equal to 0. At point 1 we have also the value equal to 0. So estimate using a second order derivative the approximate deflection at x 0.28, 25.575. Okay, so we have a's value, that means the difference between two successive nodes is 0.25. Okay, so note that y is the deflection at x. Okay, so we have to replace this equation using the finite difference approximation at first, then we have to solve this equation using the matrix form. Okay, in this next lecture I'm gonna show you how we can compute this equation, how we can write this equation in matrix form, then we can compute these equations using MATLAB. Okay, thank you very much. and I'm gonna show you. I'm gonna see you in next lecture. Okay, till then, bye bye.